All right, so up next, we've got Dr. Brent Zaprowski. He is a professor of geology and the Earth Science Program Director here at Salisbury University. So he's here to talk today about some pollen records in a project that he's conducting here on the Eastern Shore.
Okay. Yep. Thank you. Well, this is for your recording more than anything. They'll be able to hear me. That's not the issue with that. Okay, good morning. So I'm Dr. Brent Zaprowski. I teach here at Salisbury. I'm actually a geologist, believe it or not, which makes me feel a little out of place with this group. However, I'm a geomorphologist and I specialize in surface processes specifically. And so what I started to find is I have a lot of overlap with other disciplines outside the world of geology in my career. And so one of the things I've done in my career is actually look at fossil pollen. These are actually some of the more recent images from the project I'm working on now. I've been roped into this project on behalf of Nature Conservancy. I will point out right away, they're paying for all the funding for all the C14 dates here. And of course, I've had several undergraduate students because all the research projects I've done over the years with this has always been to give my students experience doing real world things. And so this is really not an exception. I did want to talk about some of the previous work briefly and then launch into what I've started with Nasawongo Creek. Unfortunately, we didn't get the data done for the talk. So there's still more to come, but at least to give you an idea of where we stand. So the first project I did when I started here at Salisbury, about 2005, I worked on a site at Snow Hill. I was contacted actually by an archaeologist named Ed Otter. Maybe knows him. He said, "Oh, this would be a really good site for you to look at." So we went out there and we cored that site. And then in 2007, we did a second site up here in Chicone Creek. As a follow-up to that one. And then now here we are many years later actually working in Nasawongo Creek. But let me talk about the other two first. So the first one was Snow Hill. This is actually along the Pocomoke River. This is actually an abandoned meander that is now turned into basically a cypress swamp. It's essentially a perched water table from what I can tell. It's actually a little bit elevated from the water level now. So I think it's almost like a ponded effect, if you will. We went out there and got a core in 2005 with these three students here, and they worked on that core. And then we went back out. This is Chicone Creek, which is a tributary of the Nanticoke. In fact, when you go over the bridge on Route 50 over the Nanticoke River, it's really the first little tributary. And we went upstream there, and this is one of these tidally influenced freshwater systems on the creek. We cored that as well. So here's the Snow Hill one. Now, this is much more interesting. And I want to thank Deborah, by the way, because you set me up so well, you don't even realize. I'm just saying, there's a lot of things I don't explain now because you just did for me. So this is the core we did. It was, as you can see here, almost a little over 4 meters long. We extract this using a vibrocore. I'll show you that here in a second. We got one C14 date, which is down here, a little over 3 meters down. And that dated to 1630 years before President, about 320 CE. And so the core seemed to be pretty consistent in terms of deposition rate. So I think we're pretty confident that we can kind of assume a chronology from that. What we found fascinating about this core then when we got the C14 days, you can see this very sudden appearance of both grasses and ragweed, and clearly way before European colonization. And this is back in 2005. One of the archaeologists on campus here then said to me, "Oh, you know, that's probably about the time that the native peoples in the area started really modifying the forests." And so that's not something I don't know was being discussed much in 2005, but that was kind of what we thought about. And so that was why we actually went to Chicone Creek. There was a Native American village there, Thank you. It's on the map. I always have a hard time pronouncing it. I appreciate that, sir. And so we decided we'd go to Chicone Creek to see if that gave us better results in terms of kind of trying to figure out what's going on here. So what I did was I basically sliced out the equivalent time slice of Snow Hill, and then we went to Chicone Creek. Unfortunately, that core only got back to about 875 years C14 or 1075 CE. So we didn't quite get past. We wanted to see the before after. And the sites are actually very different. And in retrospect now, I realize why, because they're very different forest settings. I mean, Chicone Creek's basically right on the Nanticoke River. It's really more of a tidal freshwater system with forest around, whereas Snow Hill is right in the middle of a cypress bog. So very different vegetation. So I shouldn't be too surprised. You can see here, again, I dashed in essentially the European settlement. And then you can see there is that bump in ragweed. So it's not clear to me if this is already a modified landscape at this point. That's kind of where I was stuck at that point. And then 15 years went along. I got involved in lots of other things. I tend to have projects find me. And so a lot of other projects find me in those 15 years. And then Gabe emails me, I think about a year and a half ago now, and goes, hey, I saw the work you did at the Snow Hill site, because I think, if I'm mistaken, this was published in a report for the Nature Conservancy at the Furnace Town some years ago. So he had seen it through that report, I believe. Correct me if I'm wrong, Gabe. Contacted me and said, what I'm interested in helping with looking at some fire history, something I was completely new to. And I said, sure, because I had a biology student at the time looking for a project to finish up a earth science minor. So I thought that was a perfect match. So Gabe took me out to the Nassawango site, the Nature Conservancy. We started exploring these wet areas. Because when you're trying to do long-term history, you got to find a place where you got a nice, long, wet site where you have deposition constantly occurring, but the dampness then really helps preserve the organic material, including the pollen. This was one of the sites we tried initially, and then when we actually looked at the core, realized there wasn't much to look at. This is pretty much just the bedrock sand around here, and then some silt, and then a little bit of peat on top, just half meter. So we kind of went around and we explored. We finally set on a site actually on the Nassawango Creek floodplain. I decided that I might get better luck being in that kind of depositional environment instead of trying some of these swales. So if you don't know much about Nassawango Creek, it's about 30 kilometers long. It merges down here with the Pocomoke near Snow Hill, and then all the way up here, and then right around near the Salisbury Airport is actually the headwaters. So not a particularly large drainage basin area, very low gradient. As a fluvial geomorphologist, I can tell you it's really shocking to see streams that are that flat that are able to flow. As a result, then they tend to be multi-channel. In fact, at the study site, there's kind of a break in the channels. Having waded around in the Nassawango Creek taking samples, it actually is a surprisingly hard sandy bottom with a fair amount of organic rich silt kind of mixed in. I find rivers around here to be quite fascinating, and really, and strictly speaking, it's probably classified as a blackwater type river. It has a very dark color from the tannins. So that's essentially the site we're working on. And then, of course, Nassawango Preserve is essentially through this area right here. Okay, so zooming in, this is LiDAR I pulled down from the state website just to give you kind of an idea of closer up. This is Johnson Road here. The core site's here. You can see here's Nassawango Creek. One interesting feature, and very much related to the talk here, especially considering the Carolina Bay conversation that was just brought up, these are actually transgressive dune lines. Most of this part of Delmarva is actually covered in windblown sediments. I'll go back here a second. In particular, this area is known for being topped by what's called the Parsonsburg sand, which is essentially a quaternary, late Pleistocene quaternary sandy deposit. And so during the Ice Age, there are a number of these large transgressive dune complexes that developed across Delmarva. And so we're actually kind of nestled in right at the base of one of these dunes. Now, at some point post-deposition, the creek has cut through it, but that's the remnant of the dune line. Okay, so zooming in a little further, then you can see what the site looks like. Like I said, the stream does tend to what we call a multi-branching pattern. Right here is actually this one, which does not seem to be the main flow path. It seems to be the secondary of the channels. And then you can see adjacent to that, then there's this floodplain, a lot of cypress knees here and the like. So that's basically we decided to cast our luck. Here's Gabe and I out last February. Then with the vibrocoring rig, we drive this 3-centimeter diameter aluminum tube into the ground. We pull it back up. We cut it in half. We look and see what we got. And although it wasn't a very long core, it actually ended up being a really, really interesting core. So it's a little over 95 centimeters long if you don't count the little tip there at the end. It had abundant wood fragments, which is the important thing. If you're going to try to do these studies, you have to have some timing. Otherwise, the data doesn't tell you a lot about what's happening in the past. I want to start with these two down here because these two are fascinating. They're right at the very bottom, are like perfect. You big pieces of wood at the bottom of a sediment core. You get nice chronology as a result. So we sent those off, and they came back over 10,000 years old, which blew my mind. I'm like, oh my goodness, how does this happen? This can't be 10,000 years worth of sediment, right? But there's 10,000-year-old sediment at the bottom of it for sure. Anyway, so that certainly prompted us to like, this is really cool now. So anyway, okay. So the first thing we did, of course, being a geologist, I analyzed the sediment properties. And in general, then as you can see, here's the core, right? It's about 1 meter long. We basically have a fluctuation. We have these really sandy layers. The orange is the percentage of sediment or the sand in the sample, and then the gray is the silt, and the clay is the yellow here. The blue, by the way, is percent loss of ignition, which we use as a proxy for organic content. Essentially, we burn the sample. We assume everything burned was carbon. So that works pretty good for giving us a proxy of how much organic content there is. So essentially, these are organic rich muds. You can see in some cases, we're actually pushing into the peat category. Geologists, we don't consider it peat till we hit like 50% organic content, but it's definitely organic rich, silts essentially. And then we get these coarse, medium coarse sandy layers. One real obvious one here. There's a little more subtle one up here, although the data shows very nicely where it is. So one of the things I immediately was drawn to was the sandy layer here, because as a geologist, like, well, why do we go from very quiet silt and organic muck building up and all of a sudden nice clean sands like this? So I had to do some sedimentary petrology. Essentially, what I did is I looked at the magnetic properties of the sediment, essentially, is what this diagram is telling us. And what I found was, my two hypotheses was either this is a wind-blown deposit blown in at some point from the nearby dune, or it's a fluvial stream deposit. So it was important to establish those two because they have very different interpretations. And what I found was the properties of the sand in the two sandy layers in that core were much more like the average of the samples I took from the nearby channel than they were from the average of the dunes nearby adjacent. So pretty sure that this is a fluvial layer of sand, probably during some channel development at some point. The upper layer, however, is not real obvious. My guess is that might be some kind of large shale, like 500-year sheet flood events. We got a lot of sand deposited at once. So that's kind of the sediment of the core. Now the trick then is, where is the break in time? In geology, then we talk about things called unconformities, right? This is where you have a gap in time within your sedimentary record. So somewhere in here, we jump from early Holocene to late Holocene pretty quickly. You can see then, so we have two C14 dates here, because we did two. When I got the first one, I'm like, so we tried the second one. I wanted to make sure it wasn't like old material worked into new, but clearly that couldn't be the case with two of them. So 10,190 and 10,240 years before present for the two of them there. So we then took a sample. You can see this large piece of stick here that dated a little over 1,000 years, carbon years before present. And then we got another piece of wood down here below the sandy layer, and it's about 1,800. So somewhere between here and there, there's a thousands of years of time missing. And that was really my main concern, because how we interpret the pollen and the charcoal that come out of this is going to be strongly dependent on first making sure we understand how the sediment was being deposited. So this lower layer then, and this is why I was glad Deborah brought up the Carolina Bays, the lower layer I do believe is the remnant of one of these old Carolina Bay deposits, in fact. All right. So if we look at the dating of the core, by the way, the rates are actually pretty low. I mean, we're talking at rates of, hundredths of a centimeter per year. I mean, these are really slow deposition rates. This is actually a diagram that Gabe generated for me to kind of fit the dates. And you can see there's somewhere in here, there's clearly a jump in time. So anyway, so we wanted to figure out where is the unconformity. The other problem is that this sandy layer is problematic in terms of dating. Like that sand's all coming in like one big huge unit all at once in time. And so I don't think this is continuous rate of deposition. So this is going to give us problems in terms of whatever pollen we find in there, and charcoal is going to be kind of hard to describe to as far as the timing of that event. But when you look here and up, that's a really nice consistent layer of sediment that I feel really good about what we're going to find from up there. But this problem though is where is that break in time? So if you notice, there is a slight change in color about right here, about 78 centimeters. So I believe that it is the remnant of a Carolina Bay deposit, first of all, because of its age, right? There's no way the Nassawango Creek has been operating in its current state for 10,000 years. It's a much younger stream than that. Generally, they're found all over the peninsula. This is from a more recent paper that used LIDAR to identify them for 2014. A lot of them in northern Delaware, but you can see right down here through the Pocomoke River, there's Nassawango, right? This is clearly, there's a cluster of them in here as well. And they're generally associated then with wind-blown deposits. where you get these sandy rims, and then the basins get filled with silt, which then actually makes it hard for water to soak through, and you get these standing pools of water like Deborah had mentioned before. So I think that's what one of these was at one point in its time. And so if we zoom back in on this diagram, then what I feel is probably happened is during the last ice age, the prevailing winds are coming out of the northwest. These dunes are migrating to essentially to the southeast. It would be on the downwind side here where you might get these development of these little silty pools forming. And so my thought was at one time there's a Carolina Bay in this area, and then the Nasawanga Creek at some point has eroded headward and basically bisected it. It might have had water in it one time, and the water's all drained away. And so it could very well be that we got something like this going on, where at some point the Nasawanga Creek meandered over here, basically truncated whatever Carolina Bay sediments were there, and then as it meandered back away, left behind a layer of new, more recent floodplain sediments on top. That certainly is the most likely scenario in this case. So what's interesting then is these do give us a snapshot as to what Pollen was like 10,000 years ago on the Eastern Shore, which there are not a lot of studies that have done that. So it was kind of exciting. Even if it's just a snapshot in time, it still is helpful. So anyway, so there's what we think is the unconformable contact. All right, so we started working on the pollen. Right now we're at the part where, unfortunately, my students have to go home for Christmas break. And so they got about to, I wanted to look at the bottom first. So we started at the bottom, work our way up. So this is as far as he got before Christmas started. So he'll be back soon and he'll finish this for me. We got through the most important part, which is establishing the unconformity. So again, if we look at kind of the average of the two C14 dates, here we are at 10,215 years for present. We believe then, based on the color change and the change in the sediment property, that this is probably the unconformity here. And indeed, if you look at the pollen below and above, you can see it radically changes. You can see in the below unconformity, on average, about 60% is conifers. We haven't actually separated the pines and the spruce yet. That's something we need to work on still. Hemlock, and then you can see some alder and oak and birch are the main ones here, a little bit of grass. And then after, you can see we see a huge decrease in conifers and hemlock and a huge increase in alder, oak, and some other hardwoods start to really appear. So it appears to be that is truly the unconformity. That lower part kind of gives us an idea of what was early Holocene like here in the middle part of Delmarva, and then presumably above that is some date probably around 2,000 years ago is my guess. All right, if we go back to this, there's 1,700. So it's hard. You could probably take an average estimation to figure out how far back that goes, but pretty hard to get anything firm on that. I think the most important part is going to be the upper 1,000 years or so here. So essentially, the early Holocene 10,000 year spectra, as you can see here, is essentially then a lot of conifers, some hemlock, oak, and birch, minor amounts of alder and grass, and then of course once we jump over that, we see huge increase in other things and a decrease in mostly in the conifers and hemlock. So that certainly helps support this idea of conformity. Now I'm pretty confident as we continue working our way up the core that we're going to get a really nice pollen record here. I mean, 1,000 years worth of nice high resolution pollen data would be really nice for sure. So that's what we're going to continue with. Okay, a few more minutes. Now the next step, and I think what Gabe's really been waiting for me to do, is charcoal, by the way. This is something I've never done before. I'm actually more excited to try this than the pollen. What I realized, by the way, after not doing it for 15 years, is I'm really rusty, especially on the pollen identification. So it's been kind of a struggle, but one of the sandy layers in another core, I noticed these black flecks, and I washed them out, and sure enough, that is certainly charcoal. I would like to think that someone here is way more of an expert than charcoal, and I would agree with that, yes. And I'm hopeful then that we may actually get some useful charcoal history out of this. And this then ties back to what Deborah was talking about in terms of, and even my Snow Hill core, would certainly seem to support the hypothesis, and certainly direct evidence of the management seems to be reflected in the cores. That would be my interpretation. So I'm hoping that when we look at this core, we're going to see a similar pattern to what we saw at the Snow Hill core, and then we can say more about the kind of the longer term fire history, especially when we combine the pollen data with the charcoal counts. So this is what they look like. I did just some spot samples just to try the method out with peroxide, and I was able to actually get a volume count. So hopefully in the future, you can look forward to more data coming from this project. Essentially, I assume that Gabe will continue sharing it with the rest of the folks in the audience here for sure. I do want to thank Gabe, for sucking me into this. It's been very interesting. I'm actually looking forward to really trying to do more with the charcoal, to be honest. I think there's a lot that could be done here in Delmarva with some of these cores in terms of looking at this longer term history, especially given the Native American influence. I think there's a lot to still be teased out with that. It'd be really cool to look at. So again, thanks to Gabe and the Nature Conservancy for paying for all the C14 dates. I also have to thank the Henson, Salisbury University, the Henson School of Science as undergraduate research grants that we used also to pay for the chemicals and some of the other supplies. I've had two student researchers. Erin Rosh-Nashana was my biology honor student from last fall. She graduated. And so Andrew, who is my current student, he's the one working on the pollen. He's still working on the project now. So I want to thank them, plus other students from many years ago who helped with coring as well. So I wanted to make sure I left some time for questions. Looks like I'm giving you about 2-3 minutes here. So, and really, I want to end with actually with this, which is I'm definitely not an expert in this. And I'm sure that many of you out there know a lot more about this. I would love to share my data. Just saying, right? I'm sure there's people that can interpret it better than me at this point in my career because I've been out of it so long. So feel free to take and use and interpret what I've done, and I'll share everything I have in the future. I really would encourage people to take use of the data. Again, I do it to help my students learn how to do science, but hopefully others can find the data useful too. So, okay. Any questions? Yes. Okay, so yeah. So how do I get the pollen out of the sediment essentially? Okay, so it's a series of chemical baths and centrifuge essentially. Formally, I think it's called the acetylysis method. And there's a couple out there. Generally, it's like, hydrochloric and hydrofluoric to get rid of the glasses or the quartzes. Acetylysis destroys organic, but there's a whole series of chemical baths and essentially running through filters and centrifuging. It gets down to this little concentrate that we then put drops on a microscope slide. Basically, it looks like, go back to the beginning, it looks like this when you're done on the microscope. Yeah. So that's what you end up with. You get all sorts of, the trick with working with peats, a lot of people who do this work in like lake sediments where it's much more sediment rich, a lot less organic chunks. When you work with peat, it's really hard to get it all out. I mean, you still have to deal with a fair amount of organic debris, but it's usually they stain out pretty well, especially if they've been stained properly, like this. So. Ferengi and Iverson's kind of the book I use and kind of the standard for paleontology for several decades. Any other questions? I know this is very different than probably the thing you normally hear here. Yeah, excellent. Okay. Well, that's a good question. Certainly from my reading so far, because again, this is brand new for me getting into this. Certainly, I would think the actual charcoal counts, how much charcoal you get per gram of sediment. I will tell you when we go ahead and do the charcoal, we're essentially going to do 2 centimeter increments continuously the entire 90 centimeters. We're going to have a super high resolution. I would think right off the bat that changing concentrations of charcoal in the sediments are going to be indicative of fire history right off the bat. I think that's essentially what Brush did, and Deborah can correct me if I'm wrong, Brush did in her studies. She's essentially going through and counting how much charcoal per cubic centimeter of sediment. So certainly there's that. The other thing I've been reading about, and you can see that in some of the pictures, in fact, I took, and I'm going to go back ahead, is that their shape is somewhat indicative, from what I understand, of what the material was. So you can see this is kind of more blocky, where this is a little more flaky. So there's different versions of it, and from what I understand, that can be linked to needles, leaves, sticks. So I'm still trying to get a handle on that as well. I was going to say this is a brand new voyage exploration for me, but from what I understand, those are kind of the 2 biggest things that kind of tell you, how much fire might occurred based on the amount of charcoal, and then kinds of charcoal can be useful too, from what I understand. Okay, I think that's it for my time. Okay, thank you, everybody.